radians roughly. A microradian is 1 meter at 1,000 kilometers. So it's a very small angle. And so in about 1980, the US was desperate to find out what the Russians, the Soviets, were doing in space. They wanted high-resolution pictures of their satellites. And of course, what they were getting with a regular ground-based thing was a blob. So DARPA, this technology, this adaptive optics, was just emerging at the time. And this was about the time I showed up. Well, I showed up in 1978 here in Albuquerque. And so they built this system and they mounted it on a 1.6 meter telescope on Haleakala, on the island of Maui. And this was a very specialized mount. It had 3 axes, so you could set one axis perpendicular to the plane of the orbit, and then the others would have to make smaller corrections as the satellite flew by. So they mounted a ton of equipment, literally a ton of stuff on the telescope. It was a heroic effort. It used photomultiplier tubes. The reconstructor, the thing that put the wavefront back together from individual measurements, was built with a resistor network, so it was very fast. It was an analog computer, basically. But the problem they had was it only worked for really bright targets. As we said, you have to make these measurements very quickly. If you don't have enough photons, you can't make the measurement, and so you can't get the performance. And so what we really needed was an independent light source, just like the astronomers have. They hunt around for a brighter star and they use that to guide their telescope while they're making their long exposure. We needed an artificial guide star that was bright everywhere in the sky. Well, that's kind of a tall order. Well, there was a fellow who was working on this project, Julius Feinlieb, who got the idea of using Rayleigh scatter from a laser. Rayleigh scatter is the light scattered off of oxygen and nitrogen in the atmosphere. It's like, well, searchlight is, well, everybody's been to a laser light show, right? The fact that you can see the beam is coming from Rayleigh scattering. And so his idea was shine the laser up, focus it in the sky, look at the light coming back from some faraway point. If it's a pulse laser, you range gate your receiver. You only turn the receiver on. It's just like radar. And so in the fall of 1981, he held a meeting in Boston to propose his ideas to the government. And somebody from DARPA was there. David Freed, the man that invented R0, this parameter that describes the atmospheric distortions due to turbulence, was there. I was there. And a fellow from AFRL in Rome, New York was there. So he proposed his idea, and Freed was immediately skeptical because he said it's not measuring all the turbulence. It's only measuring the stuff at lower altitude. This is what we normally would do with what we call natural guide star adaptive optics. So this is sunlight coming down from the satellite. And by the time the light gets to the atmosphere, it's basically parallel. Well, if you had this laser idea, so here's a picture of a laser beam in the sky, you're basically focusing the laser at a fairly low altitude, maybe 10 or 15 kilometers. Because if you go any higher, you run out of air. And you can't get enough light backscattered from the oxygen and nitrogen. There's no air up there. So the problem is, out at the edges of the aperture, the rays are not parallel like they are coming from the target, and so you're not measuring all this turbulence in here. And that deficiency will create an error if you use the laser to run your adaptive optics. So the question is, how big an error would it make? Well, Freed figured all this out. The very night we had the meeting, it's really interesting. Freed is a really cool guy. The very night we had the meeting, he went back to the hotel. He stayed up all night doing all the analysis, writing out all the equations. We couldn't solve them analytically. And we got back together the next morning. He said, well, I know what I need to do. He went off, he did numerical calculations, and we got back together in a month, and he said, this may not be so bad after all for small telescopes. So we were stuck. We really wanted, you know, what we really required in the long run was a 4-meter class telescope that we could correct. But we were kind of saved by the Jasons. Everybody know who the Jasons are?
No.
Anybody know who the Jasons are? This is a very high-powered academic group hired by the Department of Defense to evaluate new projects. And they have a meeting every year in La Jolla, California. And recently this writer, Anne Finkbeiner, wrote a book about it. So if you're interested, you can get the book. So in the summer of 1982, the following summer from our meeting with Julius Feinlein, we were summoned. And usually when you're summoned by the Jasons and you have a project, we didn't really have a project yet, but the best you can do is break even. You know, a lot of times people lost their projects. They lost their funding, their projects were canceled, whatever. And so Fried got up and described his theory, which he called focus anisoplanetism, the theory about having a finite altitude beacon. And the chairman of the Jasons, a guy named Will Happer from Princeton, said, so what you need is a higher altitude beacon? And you know, we said yes, and he said, well, why don't you resonantly excite mesospheric sodium? So I looked over at Fried, and Fried looked over at me. We didn't know what the heck he was talking about. Well, as it turns out, there's a layer of sodium atoms, which is sort of shown in this picture from the space station, that's 60 miles above the surface of the Earth. Here the sodium is being, and along with air glow, is being excited by the sun. And this sodium comes from meteors that enter the Earth's atmosphere and burn up. There's a little trace of sodium in those meteors. They're grain-sized, you know, pieces of sand. So the idea then was to, you could get a much higher altitude beacon, and you could sample a lot more of this turbulence for a much larger aperture by doing that. So instead of having a 15-kilometer beacon, we can now have a 90-kilometer beacon. And we can, instead of being able to operate on a meter telescope, we can operate on a 4-meter telescope. So the guy from DARPA, Rhett Benedict, immediately sponsored, this is the summer of 1982, 2 experiments. So the first thing that happened was they classified all this stuff because they didn't know how it was going to turn out, and so they made it a special access project, and there were probably 100 people in the country that knew about it, that these experiments were going on and the outcome of them. So he wanted to test both ideas, the sodium, being able to excite sodium, and to use the Rayleigh at lower altitude. And could we determine whether Fried's theory about the error that you would make using those 2 beacons was correct or not? I immediately volunteered to do the Rayleigh experiment because I had no idea how I was going to generate light that would excite sodium. It has to be very precisely on the right frequency and have certain characteristics, and we just didn't know that much about it. So Lincoln Laboratory got stuck with a much harder experiment. Both of these experiments were done in New Mexico starting in the fall of 1982, and I'm going to skip this chart and go right to this one. We called it the SOR-1 experiment. It was done out in the remote reaches of Kirtland Air Force Base of what's now the Starfire Optical Range. The place had been abandoned since the early experiments with the high-powered lasers that actually shot down a drone in 1973 there, a CO2, 100 kilowatt CO2 laser and a beam director. And the place was pretty much in mothballs. So we opened it up, and a small team, we put together this experiment. And the idea of the experiment was to point a laser at Polaris. We didn't have a telescope that was gimbal that we could point anywhere in the sky.